My birthday is in the month of December, and it's surrounded by a lot of other holidays, so it's a lot of fun. Since I'm already looking forward to my birthday this year, I decided to make a visualization of it. I decided to plot the date of my birthday for each of the last 10 years to see if I could identify any important trends about my birthday. This plot revealed something truly astounding. Every day is my birthday! This conclusion comes from accurate data, so it must be true, right? It's a common misconception that data visualizations are precise facts. As you can see in my "every day is my birthday" graph, just because I'm using accurate data, that doesn't mean my visualization communicates some objective truth. All visualizations are merely interpretations of the truth, presented through the lens of the designer and perceived through the lens of the audience. And audiences can take a single bit of information and interpret it one way, or another, or another. Even with real, accurate data, I could visualize the world in a way to convince you that Greenland is 14 times its real size. This is the Mercator map projection, used in schools across the world, and it is the preferred projection of Google Maps. It hugely misrepresents the size of regions closer to the North and South poles. Here, Alaska appears to be 3 times the size of Mexico, when it is in fact marginally smaller. There is a wide gap between numerical information and how we interpret that information. Let's take, for example, some great analytical images generated by Dr. Mark Newman at the University of Michigan for the 2008 United States presidential election between Barack Obama and John McCain. Americans are especially familiar with this image, where each state is colored in by which party took most or all of its electoral votes. At a glance, it seems like America was split pretty evenly between the red party and the blue party. But the amount of red ink on this map is not proportional to the number of electoral votes that went to the red party. It's proportional to the geographic size of each state. Montana adds a huge amount of red ink for 3 electoral votes, while the relatively small New Jersey adds 15 votes to the blue party. So Dr. Newman rescaled the sizes of the states by their population. Now you can see the huge populations of the Northeast and the small populations of the Northwest start to be more accurately represented. The amount of blue ink more accurately represents the outcome of the election. We can see this same effect on a smaller scale if we look at how each county in the country voted. Lots of wide open rural farmland went to the red party, but when it gets rescaled, we can see how urban areas dominate the outcome of the election. This tells a narrative of a divided country. People with very different opinions are living right next door to each other, right? Well, not if we color them by the strength of a party's dominance. We can see that very few areas of the country are actually strongly for the red or blue party. All these examples relied on the colors red and blue, which we can critique as well. Red is more noticeable to the human eye, so the red ink is not equal to the blue ink. But red and blue have been established as a convention. Can you imagine how confusing it would be if we violated convention by swapping the red and blue parties? In 2D information visualization, there are some guidelines the visualization community has agreed upon for what a visualization should look like. For instance, it's largely considered a bad idea to use a pie chart because humans are bad at judging 2-dimensional attributes like area. Can you tell which wedge is the largest one in this chart? There are 3 large wedges that all seem likely candidates. A better way to show this might be this stacked bar chart, which still demonstrates parts of a whole, but reduces dimensions mapped to data from 2 to 1. Now we're only looking at the height of the bar instead of width and height. In 3D scientific visualization, similar guidelines are less well defined. The shapes being rendered in scientific visualizations are significantly more complex than in information visualization, so it's harder to isolate universal rules. This is why it's especially important to understand the concerns of the information visualization community so that you can interpret their criticisms from the perspective of a particular scientific visualization. 3D scientific data variables can lose their meaning if you compress them into a single dimension like a stacked bar chart. But sometimes we can make things clearer by compressing 3D data into 2D by taking a slice through it like this. Ultimately, it's important to understand that higher dimensional spaces are harder for people to intuitively understand, so do not add more dimensionality into your visualization just for the sake of being flashy. 3D spatial data is usually best represented in 3D, but keep in mind that it comes at the cost of a higher cognitive load. This visualization was meant to show that Hurricane Harvey dropped nearly 3 times the water over Houston as Hurricane Katrina did over New Orleans. But intuitively, the larger sphere does not feel even close to 3 times larger. The impact of the data is minimized by the visualization rather than being highlighted by it. One common guideline in 2D visualization is called the principle of proportional ink. This principle suggests that a visualization should always keep the size of a colored region proportional to the value it's representing. This 3D pie chart violates the principle of proportional ink because the raised side of the chart contributes more blue ink than is proportionally accurate. But also, this 2D bar chart violates the same principle because the bars continue beneath the zero line of the chart. So why is this relevant to a 3D scientific dataset? Managing exact proportions is going to be impossible. 3D scenes have a vanishing point which makes nearby objects larger, so as the data and the camera move, objects will change size perceptually and at a different rate than they change in physical size. However, the principle of proportional ink does offer some guidance in the sense that we can avoid overemphasizing the wrong thing. If our scene has one feature that's larger than the other, we can maintain a sense of the proportion by keeping the larger object closer to the camera or by keeping an equal distance between the two. Another guideline for 2D visualization is to always start your y-axis at 0. For example, if you look at this bar chart, you might get the impression that the difference in values between these two bars is large. But it might actually be small when you notice that the y-axis didn't start at 0. Starting the y-axis at 0 helps give your viewers much needed context for the meaning of the data values you're rendering. However, this rule is not always relevant and it doesn't always help provide context. This line chart is called the Keeling curve. It's famous for being early evidence of global warming. You can see that the y-axis does not start at 0. The reason for this is that a small change in atmospheric carbon can have a huge impact on the climate. If the y-axis started at 0, the slope of the line would be merely horizontal. It's also not reasonable to expect atmospheric carbon dioxide will ever get close to a value of 0, so showing such a broad range strips this data of its context completely. It might be reasonable to reinterpret this y-axis rule more generally as ensure that your audience has the appropriate context. In 3D visualization, this might mean that you want to provide descriptive labels, or you might set one dataset against another dataset that provides a meaningful background. For instance, this visualization of data collected by the Earth monitoring satellite Terra is set on top of a globe with NASA's blue marble imagery. The satellite data would be hard to place geographically if it was simply mapped onto a black sphere or laid out as a flat streamer. The 2D visualization community also has guidelines regarding choices of color, interactivity, and multiple side-by-side images being presented together, all of which can certainly benefit 3D visualization as well. 3-dimensional visualizations will inherently be more cluttered than 2-dimensional ones, though. The default state of a 3D visualization before it has been designed is one of clutter and opaqueness. Because of this, there are some guidelines that are not well encoded by the 2D community. The scientist who shared this data of the outer third of the sun told us that we should find rolling waves of magnetic activity around the sun's equator. We dropped streamlines into the data over and over and over again, trying to find the magnetic waves with no luck. Finally, we found the waves after flipping a negative sign into a positive. The best advice we got on how to represent this data wasn't from the visualization community, but from the scientist. There are also no clear rules about how to pace time-evolving data. If you play back an evolving dataset too quickly, your audience won't be able to understand what's changing. If you play an evolving dataset too slowly, your audience will forget how it started. Choosing a pace for your time-evolving data is something that's harder to encode in a rule of thumb. There are some areas of 3D visualization design that aren't even well understood by experts. For instance, the benefits of cinematic presentation of data are not well studied. Methods for visualizing error in 3D datasets is only starting to be investigated. And side-by-side comparisons of different models showing the same types of 3D science are sparse. Until there is academic consensus, these types of design decisions rely on a visualization designer's intuition. Your ability to meaningfully critique visualization choices will improve with practice, and ultimately prepare you to be a better visualization designer. Fun fact: Sometimes visualizations are so bad, you can't help but wonder, wouldn't it be harder to make these mistakes than to not make them?